Hello, my name is Byung-hyun Yoon. I will be presenting our work on targetless multiple camera and LiDAR extrinsic calibration using object pose estimation. This work was funded by Electronics and Telecommunications Research Institute and BK21 Plus program. And this work was done in collaboration with me, Hyunwoo Jung, and our advisor, Kang-sun Choi from Korea University of Technology and Education. Before presenting our work, let's see previous work shortly. There are mainly two types of exchange calibration. First is target-based method. This method finds exchange parameters using specific target. Usually, arc marker and planar patterns are used. Second is targetless method. This method finds exchange parameters using geometric features. Usually, edges, lines, planar regions are used. There are some features of two types of calibration, like pros and cons. In target-based method, they need specific target. So usually, these methods are laborious and time-consuming tasks. And these methods show good results, but not easy to recalibrate. In targetless method, geometry features are used like lines, edges, a trihedron, and planar regions. This method is easy to recalibrate, but it needs a lot of data to find correspondence. Motivated by other calibration method and object pose estimation method, we wanted to solve extrinsic calibration problem using small set of data without a specific target. So we wanted to use common objects like chairs, table, and couches. For this purpose, we use multiple cameras and one LiDAR. Each camera captures only one picture and LiDAR scan only one time. So in our work, only 3 images and one LiDAR scan was used. This is overview of our work. There are 3 main steps: pre-processing, initial calibration, and calibration refinement. In pre-processing, 2 point cloud and instant segments are obtained. One point cloud comes from images and the other comes from LiDAR. In initial calibration, initial parameters are obtained using ICP registration. In calibration refinement, with initial parameters, instant segment, and object point cloud, object pose estimation was performed. After that, we can get final calibration parameters. I will introduce whole step by step. First step is data acquisition. As mentioned before, 3 images captured by 3 cameras and 3D point cloud was captured by LiDAR. First step of pre-processing is color correction. Color distribution of image 2 is transformed by CPD registration to color distribution of image 1. With this step, performance of following process was improved. Next, to determine registration regions, object segmentation was performed. In our work, 2 segmentation methods was used. One is a semantic segmentation network, and the other is superpixel-based segmentation. Semantic segmentation network distinguishes useful object regions in whole images. Superpixel-based segmentation method was used for clear boundaries of segments. After 2 segmentation methods, 2 results are combined by overlap criteria. So after object segmentation, we can get object segments with clear boundaries. Inside of pre-processing, SFM-based 3D reconstruction, 3D point cloud generated with images. First, feature extraction and matching was performed, and then 3D point cloud obtained. But this point cloud was non-useful, so with segmentation mask, generated point cloud was filtered. After that, to remove noisy points, range search technique was used. Finally, point cloud related to object was obtained. Last step of pre-processing is point cloud segmentation in LiDAR. LiDAR captures 316 degrees of environment, so points in out of range have to be removed. First, ROI was applied. In our research, 60 degrees of ROI was used. Second, large planes are removed, like the wall, the ceiling, and the floor. And then, remaining points are simply segmented into object point cloud with Euclidean distance. In initial calibration, initial parameters are determined. In this step, two point clouds are used. One is SFM point cloud and the other is LiDAR point cloud. Two-point clouds are used for ICP registration. Fourth, SFM point cloud is up to scale. So scale of SFM point cloud is roughly estimated using distance between objects. The scaled SFM point cloud and the LiDAR point cloud are matched using ICP registration. After registration, initial parameter was determined. Look at the right figure. Extrinsic parameter between LiDAR and camera was roughly estimated. First step of calibration refinement is 3D mesh model generation. Object pose estimation method used in our work needs 3D meshes. So for each object point cloud, 3D mesh is simply generated. Second step of calibration refinement is appearance model generation. All parties in mesh model needs foreground and background color model. In used object pose estimation method, the color model was given and then updated with pixels around the projected position. But in our research, the color model was not given because we don't know what objects are used. So we have to make two color model. First, we can think of creating a color model in a projected location. But in this time, the extrinsic parameter was roughly estimated, so easy to make wrong color model. To avoid this problem, we used object segments for generating a correct color model. Look at the top middle figure. In roughly estimated mask, background was contained, so wrong foreground color model was generated. But look at the bottom middle figure. In object instance mask, background was not contained, so more accurate foreground color model was generated. Last step of calibration refinement is object pose estimation. We generated the mesh model and appearance color model. Object pose estimation can be performed. In this time, we repeat 6 iterations. In iteration 1, extrinsic parameter roughly estimated. For in iteration 6, roughly estimated parameters are refined. This is the result. In this research, the 3 extrinsic parameters between LiDAR and cameras are independently calculated. Both of dataset shows good, refined result. This is the environment of a synthetic dataset. There are 2 paths of camera. In each path, elevation and azimuth degree is increased from 0 to 19. And this is the synthetic data, so we can modify some properties of data. We modified our dataset in 2 aspects. First, in LiDAR point cloud, noise was added. We increased LiDAR noise from sigma value 0 to 0.08. Usually, LiDAR sensor has noise on sigma 0.02. Second, we change the number of objects. From 2 objects to 4 objects, we evaluate our performance. This is the result of a synthetic dataset. First row is result from amount of noise. Two dataset according to the elevation and azimuth degree shows good result until 20 degrees. But after that, accuracy is decreased. And result in 75 elevation degree shows lowest accuracy, because usually semantic network was not trained with bird's eye view images. Second row is number of objects. Experiment shows lowest result with 2 objects. Because 2 objects not satisfied 3 degree of freedom of rotation. 3 objects shows good result better than 2 objects in 2 synthetic dataset. 4 objects show highest accuracy. So in this method, we have to use at least 3 objects. This is a summary of contributions. We developed a targetless multiple camera and LiDAR calibration method that estimates the extrinsic parameters successfully using object pose estimation. We propose a simple yet effective method that provides an initial calibration parameters. Based on the initial calibration parameters, corresponding objects obtained from multimodal measurement are matched. Consequently, the color appearance model corresponding to the object mesh model can be created appropriately. We address how to apply the correspondence between partially available object model to region-based object pose estimation for object tracking. Thank you so much, and if you have any question, please feel free to ask me question at this email.